Thank you both to Brian and to the Lab Medicine Grand Rounds Committee. I appreciate the opportunity to come and talk with you about prenatal aneuploidy screening in the genomic era. I have no financial disclosures, but I should mention right off the bat that I have been known to have some personal stories that will get populated throughout the course of my talk that'll help all of us stay awake and maybe a little bit more focused. So the outline of what we're going to talk about today, we're going to start with foundations. I've borrowed that from the MLS course, which is really, we're going to talk about some of the fundamentals related to cell-free DNA screening, and then talk a lot about the test methodology, because this is really some of the exciting work that we've done here, and then finish up with the clinical testing portion. So no talk that is talking about cell-free DNA in prenatal diagnosis would be complete without a picture of Dennis Lowe, so he's shown here. With Rosa Chu and Alan Chen. And so this is a quote from a paper that he wrote in Clinical Chemistry in 2015. So when he was looking to get a faculty position, he went back to the University of Hong Kong when it was transitioned back to China. So he noticed that in 1996, there were two papers that had been published in Nature Medicine, and that was regarding the presence of tumor DNA in the cell-free fraction of blood obtained from cancer patients. And just as an aside here, we actually have known about that since 1948. So that wasn't a new discovery at that point in time. I love how he continues. So he thought a cancer growing inside a cancer patient was somewhat analogous to a fetus developing inside its mother's womb. I felt that way at times when I was pregnant. And he had yet to see a cancer that was as big as an 8-pound baby. And really, the rest is history, so to speak. He made the landmark discovery that was published in Lancet in 1997, that you can find fetal cell-free DNA in maternal blood. And prior to that, it had really not been known. We would clinically make a slight modification to his title here, which is that we would cross out the word diagnosis and exchange it with screening. And we'll talk a little bit more about why that is. But it's really important to separate diagnostic testing from screening testing, particularly when we're talking about prenatal aneuploidy. So as with many things in molecular biology and genetics, we have a lot of different jargon that's involved. So what is cell-free DNA? There's a lot of different acronyms that are used. I'll try to be consistent. So cfDNA stands for cell-free DNA. So those are just DNA fragments that are circulating freely in the bloodstream. That can be contrasted with CFF, or cell-free fetal DNA. That's the placenta-derived fraction of cell-free DNA that can be found in a pregnant woman's blood. And then whether you call it NIPS for non-invasive prenatal screening or NIPT, as it was initially called for non-invasive prenatal testing, that really refers to the test methodology itself. It's really an umbrella term to discuss cell-free DNA prenatal aneuploidy screening that's been clinically offered since 2011. And I will try not to use too many different terms. There are currently 3 dominant, I would say, clinical applications of cell-free DNA. And it's important to recognize that the biological analyte that we're looking at is the same. Now, where it's coming from is different in each of these different contexts. But we can learn a lot from doing the different types of testing. So we'll be talking today about cell-free DNA prenatal screening. But in the somatic context, circulating tumor DNA, also sometimes called liquid biopsy, is really hot. It's really exciting, a way potentially to be monitoring cancer, whether it's diagnosis or treatment or resistance, by doing a blood sample, just a blood sample, as opposed to doing a biopsy. And so right now, there's not very many of these people who are talking to these people. In our clinical laboratory, we're doing actually both tests, and it's been really informative for both aspects of that. And then in transplant surveillance is another hot area for cell-free DNA testing. And it's really, again, looking for DNA that's released from the organ that's been transplanted into the patient that's then going to be freely floating in the recipient's cell-free DNA portion. So I mentioned before that cell-free DNA, it's placental derived. And what we're doing in this testing is using it as a surrogate for the fetus. So as the fetus is developing, we from the trophoblast-derived DNA, which is shown here in white, so that enters into the maternal circulation. It's very intentional that you have mostly purple or maternal DNA that's shown here. Because that's what most of it is. So around the gestational age of 10 weeks, in the range of 90% of the cell-free DNA that you can find in maternal circulation is from mom. So only about 10% of it, on average with a wide standard deviation, is actually going to be from the placenta, or what we would call fetal DNA. We don't know that much yet about cell-free DNA as a whole. So in healthy, non-pregnant individuals, the concentration of cell-free DNA is around 1.6 nanograms per milliliter of plasma. So that's very low relative to other things. If you're thinking about doing a Southern blot, you're using 5 micrograms of DNA for a test like that. Usually when we're doing our targeted gene capture for Oncoplex or BRCA testing, for example, we're using in the hundreds of nanograms to start that library preparation for next generation sequencing. So here we're starting with a tiny fraction of that, which is important. And what we have found, mostly initially from the pregnancy patients, is that we have a very rapid clearance. So the half-life is in vivo, the half-life is only 16 minutes. And if you sample a pregnant woman postpartum, by 2 hours, you can no longer detect the fetal cell-free DNA. So it's cleared that rapidly, which is really advantageous when you think about a method that you're going to want to monitor during one pregnancy, and then you're going to want to monitor potentially in another pregnancy as well. So we don't have cell-free DNA that's going to be continuing in the woman's bloodstream. There can be very rare nucleated cells, which can sometimes trip people up, but we're not looking at the nucleated cellular DNA in this test. We're going to be looking specifically at cell-free DNA. And we're going to get that cell-free DNA from the plasma portion. Early studies had also looked at using serum, and people were excited because you could get higher concentrations of DNA from serum. That must be better. But it turns out what you're actually sampling when you get that higher amount of DNA from serum is mom's white blood cell DNA. We don't want to look at mom. The whole point of doing this test is that we want to see what's from the fetus. So serum has really been quite rapidly abandoned as an analyte for doing this testing. This is a study that looked at the fetal fraction across gestational age. So gestational age is down here along this axis, and then the fetal fraction as a percentage is on the y-axis. You can see first off the bat that there's a very wide range. And so when we're looking from 10 weeks out to 36 weeks, there's a significant difference in the mean, as shown by the black line. But there's also a significant amount of difference from one patient to the next. It's not really until about age 22 weeks, gestational age 22 weeks, that you start to see a more rapid increase in the fetal fraction. So looking in this range, which is when we're going to predominantly be doing the cell-free DNA testing, there's not a significant difference from 1 week to the next. So it's a pretty modest pace of DNA that's going to be released into the bloodstream. And this was the largest study thus far that we have. But others have looked at this and seen similar trends as well. So once you reach, particularly in the 3rd trimester, you'll get more cell-free DNA, but you'll have other clues as far as when we're thinking about aneuploidy status by the 3rd trimester. Looking at the different methodologies that have been used and are continuing to be used in aneuploidy screening, there's a wide variety of different ones. If the slide looks busy, that's because we have a lot of different tests that are used. And what's shown on the bottom are the screening tests. So in green are some of the ultrasound measurements that we're doing. I apologize in advance to our immunology colleagues in the immunology lab who do all of the serum screening. I've abbreviated it as 1st trimester maternal serum screening and 2nd trimester maternal serum screening. There are a lot of different permutations of that testing, and that impacts the detection rate. But what's shown over here in the blue color is the cell-free DNA screen, which is typically not used until about 10 weeks. That's when you, on average, get enough cell-free DNA from the fetus, it's actually of the placenta, that's going to be released into maternal bloodstream. What's nice is that you can continue to look at it all the way until the baby's going to be born. Remember, right after the baby's born, it's going to be a very rapid decline that you'll see. Diagnostic testing is what's shown on the top in red. So it depends on the sampling that you're going to do. So earlier in the 1st trimester, you would do chorionic villus sampling. And then in the 2nd trimester, you would do amniocentesis. And diagnostic testing is very important in order to confirm a screening result, wherever you're getting that screening result from, whether it's maternal serum screening, cell-free DNA screening, or ultrasound. The point is that those are screening results that need to be confirmed. So I'm only going to show one slide that has this data on it so that we're not overwhelmed with different statistics. But these are some of the tests that are used with maternal serum screening, plus or minus use of ultrasound, so the quadruple or the full integrated. So the detection rate, it's what's shown in this column, so the sensitivity of the test. You can see that depending on the permutation and specific aneuploidy that we're trying to detect, that ranges from somewhere from 75% up to 90%. What's really important is to note the false positive rate. So, for example, looking for trisomy 21, that's been hard-coded at 5%. Right? So 1 in 20 women who screen positive is a false positive. That's a pretty significant portion when you apply this to hundreds of thousands to millions of women. And that causes a lot of angst among patients. And then we have to do a lot of diagnostic testing for follow-up for those false positive results. One of the advantages, and that's what leads to this low positive predictive value. So even if we can get into the 90% using some combination of ultrasound testing and maternal serum testing, it's not going to be good enough if your false positive rate is in the multiple percentages. So cell-free DNA offers some advantages, both in the detection rate, but really more significantly in the false positive rate, where we've dropped this by orders of magnitude. So the false positive rate by cell-free DNA is very low. That doesn't mean it doesn't happen. Any test that we're going to do across hundreds of thousands of women, we will have false positive and we will have false negative results. Period. That's end of story. I'm not going to tell you different, and I hope that the companies also aren't telling you anything different. The positive predictive value is going to vary based on the population that you're screening. So initially, cell-free DNA was offered in high-risk populations, so women who had a higher likelihood of having aneuploidy, most commonly advanced maternal age. That's when I received my cell-free DNA test, was because I was of advanced maternal age, but also other indications like there's been recurrent abortion, or if there's spontaneous pregnancy loss. There's also chromosomal translocations that predispose you towards having aneuploidy. So the numbers as far as prevalence that are shown here are really mixed. So we have looked at cell-free DNA testing in low-risk populations, in the general obstetric population, and the performance is actually quite good, higher than perhaps has been expected. So this is a recent meta-analysis of dozens of different studies, actually over 20 studies. And so it includes over 225,000 women. In order to include this study in this meta-analysis, at least 85% of the pregnancy outcomes had to be known. So we have at least some indication of what happened with these pregnancies. It's not just screening data. So from those women, almost 2,000 of them were trisomy 21, had a fetus that was trisomy 21. All of those patients tested positive. There were 0 that tested negative. Okay? This is what's published. So out of the 220, almost 224,000 who were unaffected, we had most of those testing negative. There were 66 false positive test results here. So remember, this is a mixed population, high risk and general obstetric population. So my back of the envelope calculations down here are that the test is performing pretty well. There have been studies that have looked at this prospectively in a general obstetric population, and we've seen similar numbers. So it's performing quite well, which is important because there are some groups that are advocating for using this in all pregnancies. And when we look at what's actually happening here in our clinical population, we see that there is increased adoption outside of that high-risk population. So unexpected directions is when I came to UW, I can't say that I'm new here anymore. I think that I'm here almost 3 years. I've finished the time where I can say that I'm new to UW. But I was coming from WashU, and John Tate was my division director, and I was very excited, and I went to him and I said, I want to spearhead a development project. What can I do? All sorts of exciting things are happening here. What can that possibly be? And he said, well, we need somebody who's going to take on prenatal aneuploidy screening. And I said, sign me up. That's very exciting. And it really brought me full circle back to this paper that was, as a very new clinical chemistry fellow at WashU, I presented this at a journal club. And it was a critical journal club. People critiqued this paper. So it was from Dennis Lowe's group. He published a whole bunch of papers in clinical chemistry and a number of other journals, really trying to look for what could we have as a clinical test to detect fetal aneuploidy. And so this, in the people that were in the room that critiqued my analysis of the paper, which is I said, this is exciting, this should be a clinical test. And they said, absolutely not. There's no way that this could be a clinical test. Presented that in 2008. It went live in 2011. In their defense, It was using methylation markers, the specific study. Dennis's group published a whole bunch of additional papers that were not looking just at methylation markers, but at the time, we didn't have next-generation sequencing that was widely available, certainly not in the clinical context, and so we weren't really able to get sufficient sensitivity. So a lot of methods tried to get at epigenetic modification, and I remember some people saying, well, we're going to bleed women dry because it required 2 tubes, right? That's actually now often standard for what we're doing. So that was my initial foray, and people said, no way, this can't possibly be a clinical test. So my message to the trainees is, have a grain of salt in the back of your mind when someone tells you that a test can't possibly be implemented clinically. From a popular press genome web, I pulled this statistic, which is not only is this a viable clinical test, but insurers actually are projecting that non-invasive prenatal screening will grow to 6.8 billion by 2022. It's a huge market, a huge market. And we are an academic laboratory, which is different than all these commercial entities. So there are a number of different commercial entities who are offering this clinical test. Why should we offer it? Why should we duplicate the services that are actually already being offered in these commercial markets? To date, there has not been an academic-developed cell-free DNA prenatal aneuploidy screening test, period, end of story. It's offered at some academic institutions in collaboration with commercial companies. That's not something that's been independently evaluated, developed, spearheaded, analyzed, which is different than what we're doing. So everything that we have done has been developed here in-house. It's all custom analysis. And why we should do this, besides the fact that it's cool and an important clinical service, I pulled from the Obstetrics and Gynecology, our new lab medicine website, and then the UW Medicine page, right? The first is for patients. This is better clinical care. Our test, we've been able to validate relative to other clinical tests that are commercially offered, and we've improved upon the algorithms that are being used. For research, we're taking an innovative approach. When we see a method or a test, a case that doesn't match what we're clinically seeing, we change what we're doing. We have a rationale for doing that because we care about our patients here at UW. We know what the clinical outcome is for our patients, right? We're not doing this across hundreds of thousands of patients at all. And for education, our trainees will tell you as they come onto service, they're immersed right away into analyzing the data for cell-free DNA prenatal screening. And that's not just the trainees within laboratory medicine and pathology. It's also within maternal fetal medicine and genetics. So this is really, it meets all 3 of our big missions for the institution. Okay, let's move into the methodology, the exciting part. So all cell-free DNA methods rely on next-generation sequencing or massively parallel sequencing. What they also all do is start by isolating total cell-free DNA. Why does that matter? Because more than 90% of the sample is coming from mom. That's important, okay? We don't have a way to say, I only want baby's DNA. There isn't a way for us to do that analytically at all. So from there, you can either do whole genome sequencing. This is what we do in our laboratory, or you can do targeted sequencing of selected loci. You can do that in different ways. You can look at SNPs, or you can do an amplicon-based sequencing and then sequence from there for stretches of whatever chromosomes you want to look at, right? So you can do, most commonly where we started with was 13, 18, 21, and then the sex chromosomes. But if you want to look at microdeletions, duplications, you would then target those regions. From there, you can do either relative chromosome dosage analysis. This is, again, what we do in our laboratory. To date, although we have gotten a whole genome analytically, reagent cost to be less than $1,000, in order to be able to look at, to do the allelic ratio discrimination, you would need, it's cost prohibitive. You would need to do it pretty deep in order to get that sequencing coverage. And so really all methods that are doing whole genome sequencing are doing a relative chromosome dosage. So we're looking at the dosage of this sample relative to a reference set of samples. If you're doing targeted sequencing, you can do either relative chromosome dosage or an allelic ratio analysis. In order to do allelic ratio analysis, you have to know what you're comparing to, right? So you have to analyze what mom's DNA is. So conveniently, when we're getting a buffy coat, right? So you get the plasma portion and then the buffy coat, you can get mom's sample right there. So it's built in one analysis step. But it is a separate analysis that would be done for those 2 specimen types. So my very high-tech schema here. So in a euploid state, for chromosome 21, you would expect to have one copy that's come from mom and one copy that's come from dad. And then if you're doing a case of trisomy 21, again, by allelic ratio analysis, you would be looking for, are 2 of those alleles from mom, or are you getting 2 of those alleles from dad? And remember, you have sequenced mom, so you know what her genotype is. So that's what you're comparing across. And it's tens of thousands of loci that you're using for that allelic ratio analysis. What we're doing is what's shown here, which is that you're looking for the relative dosage of chromosome 21. So the sample relative to your reference set of samples. We'll talk about what that specifically looks like. It looks simple, right? You're looking for a 3-to-2 ratio. Do you have 3 copies of chromosome 21 to 2 copies of your reference? Remember, the problem here is that 90% of the sample is from mom. So 90% of it is euploid. You have to be able to pick up that 10% that's coming from the fetus in the case of a trisomy. And that's if it's an aneuploidy state across the entire chromosome. So how we went about establishing our baseline is that we collected, over 18 months, we collected a second tube. I haven't mentioned some of the people that have helped me in the lab. So Christy Smith was meticulous in her specimen processing, and she extracted all of these samples for us. So we had 1,432 total samples. We haven't analyzed all of those because, as you might expect, most of them are negative. That's how this works with aneuploidy screening. But in order to create our reference set, we had 403 that were we confirmed to be non-aneuploidy samples, and that was relative to the outside lab, where these were clinical tests that were already going out the door. Because of the timeline, we actually ended up knowing the outcome of those pregnancies as well, because development never goes as quickly as you would like it to go. But 210 of those were pregnant with an XY fetus, 193 were pregnant with an XX fetus. And so this is work that Steve Salaponte and Bryce Colbert and I did, looking at how are you now going to analyze the data. So you've sequenced it, you've done whole genome sequencing. We'll just say that that magically happens. That was work done by Mallory Baytal in our lab. So you've magically sequenced the whole genome, and now you need to analyze your sample relative to your reference alleles, your reference baseline samples. So we divide the chromosome in 2 different sized windows, cleverly called a large bin and a small bin. So the large bins are 1 megabase, so 1 million bases. Cytogeneticists are used to thinking about 1 million bases at a time. In genetics, we're usually thinking about a gene at a time, not 1 million bases where you have lots of genes that are incorporated in there. So we divide the chromosome into large bins of 1 million bases, and they overlap by 50%, so they're staggered. And then we also have small bins. So each large bin, we're dividing into 10. So that gives you 100 kilobase small bins. So why are we doing that? So that we'll be able to determine for this sample relative to our reference samples, what's the status at positions all along the chromosome. So looking at chromosome 1, it's almost 250 million base pairs. So that means we have 373 large bins. Remember, we're overlapping them by 50%. And then we have almost 2,500 sequential small bins. Chromosome 21, which is, of course, a lot smaller. So there we have 48 million base pairs, so that leads to 71 large bins, and then 480 sequential small bins. So we talk about big data. This fits in that category. It's a lot of data that we have to analyze. We also need to know the fetal fraction in the pregnancies. Those that are from a pregnancy with an XY fetus are actually relatively easy. I think that this is intuitive, that if you have a pregnancy that has an XY fetus, you can look for the presence of Y. So any reads that are mapping to Y, the portions of Y that are unique, there are some regions that are common between X and Y, but if you mapped those reads, then it's easy. That's your fetal fraction. And that actually is a very nice relationship and one that we exploit. Not all pregnancies are XY fetuses, right? So, and of course, a priori, we don't know whether it's going to be an XX or an XY. This is done at 10 weeks gestational age before you're going to be able to do any of that sort of information, unless you do an invasive method and from there do karyotype or another cytogenetic technique. So if we have a pregnancy that has an XY fetus, we look for the Y chromosome reads. If we have a pregnancy that does not have an XY fetus, then we exploit a difference that has to do with the different size that's coming from the cell-free DNA from mom and the cell-free DNA from the placenta. And this was actually work that came out of Dennis Lowe's group as well. So I was at an AACC meeting in 2015, so this was in July, and he had won the Wallace Coulter Award, and he was giving a talk. And as I'm listening to his talk, talking about how you can use this for tumor, right? That's very exciting. We care about circulating tumor DNA. We want to do that. But you can also use it for fetal DNA, right? It's the same relationship. So fetal DNA is also smaller than the maternal cell-free DNA. So I was texting with Steve, and I came back, and we started working on it. And Bryce and Steve, the rest is history, so to speak. But the biology of it is still not well elucidated, but the reality of it, and this is an idealized image, I'm going to show you real data that doesn't look as pretty as this, but healthy cell turnover in mom's circulation, it mostly comes from hematopoietic cells. So it peaks at about 167 base pairs, okay? And then cell-free fetal DNA, right, so that's coming from the placenta, is smaller. So the size of that stretch of DNA is about 147 base pairs. And if you think back to your molecular biology textbooks or a review that you've read recently, right, we're going from the DNA packaging all the way up here into the chromosomes. What we really want to focus in here are the nucleosomes. And so this is where we're wrapping the DNA around the core set of 8 histone proteins into a nucleosome. That magic number in the nucleosomes, it corresponds to 147 base pairs. We have a histone, an H1 protein, that binds here to what's called the linker, the spacer DNA. It's a linker itself. That's 20 base pairs. So, if you're doing your math at home, the maternal cell-free DNA seems to correspond to the nucleosome plus this linker of 20 base pairs, whereas what we're getting from the fetus or the placenta, but it's the same source, would be the DNA only that's wrapped around the nucleosome. Biologically, why is that? I can't answer that question because we don't know. But it likely has to do with the configuration of the DNA. Is it open? What's the chromatin look like? We're still determining that as a field. So here's what it actually looks like. So this is from cell-free DNA from a healthy male. And we're looking at the read length down here on this axis and the read counts on the y-axis. You'll note that the read counts are low overall. You're going to see that that's going to be common for all of the data that we're going to look at. That's because we're doing whole genome sequencing. So on average, across the whole genome, we're somewhere between 0.5x and a little over 1x. So that means on average, can I tell you your strings of A's, T's, C's, and G's? Absolutely not. I'm not sampling enough to do that. When I'm looking across 1 million bases for those large bins, I have on average 500,000 of them that are represented. So that gives me a lot of confidence in what that bin is doing. Is it at an increased rate or a decreased rate relative to my reference baseline set? So cell-free DNA from a healthy non-pregnant female looks similar. So the predominant peak is over here at 167 base pairs. There's this 10 base pair periodicity, and that likely corresponds to the machinery that we have for programmed cell death for apoptosis, which cleaves DNA in 10 base pair units going down. But again, this is not well elucidated to date. Okay, so here's the real DNA view. It's not as pretty as the idealized view. But this is a fetal fraction from a woman pregnant with an XY fetus. So it was a euploid pregnancy, nothing wrong with it. She just happened to have a high fetal fraction. It wasn't even that it was particularly late in pregnancy. So there's normal variation. So this was 40% was from the fetus. And so when I say that what we're looking at for the smaller read length, it's this population down here. So that's slightly increased for what's coming from the Y chromosome. Relative to if we look at the 167 base pair, the pink line is what's coming from specifically the X chromosome, which, because mom has 2 X chromosomes, that's going to be overrepresented relative to the entire sample. You don't believe me, but this is robust. It's actually reliable. So Bryce ran 50,000 different algorithms, and we picked the one that did the best. So what we used as training was XYs. Well, first, we started with our healthy males. They're 100% XY. So then we started to do dilutions and modeling from there. And then we used our pregnancy samples that were pregnant with an XY fetus, again, for training the algorithm. Where can we get the best discrimination? And it's not straightforward. But it's how we can determine for XX fetuses what the predicted fetal fraction is, just based on the relationship between the size distribution of there versus the 167 base pairs. So why do we do that? Because we need to know that we have fetal DNA that's present. So we require for our test that we have a fetal fraction of 4%. If we don't have 4% that's present, either by the calculated Y reads or by the prediction that I just delineated, then we issue an indeterminate report. And we say, please send us another sample unless that's not clinically indicated. We don't additionally charge for that. In our validation cases, we ran over 500 cases altogether when we were doing our validation, both the baseline and other samples. The average fetal fraction was about 13%. And so most of those women were in that 10 to 13 or so week stage. But it's very important that you know if you have fetal DNA present in the sample. Because if you don't, you'll report back 46XX because that's what mom's karyotype is, right? There would be no indication, so it would be potentially a false negative. There are some biological factors that can affect your fetal fraction. So one of those, this seems to be the most prevalent from what we've looked at to date, is the maternal weight. So the proportion of low fetal fraction pregnancies increases with a higher maternal weight. I personally never think in kilograms, I think in pounds. But looking over here in kilograms, if you get to 160 kilograms, it's about 350 pounds for those of you that don't want to do that math in your head. So with that red line being at 4%, about 50% of those samples are going to fall below. And that's based just on the fetal fraction. So as you have an increased BMI, and it is actually BMI, not just weight, but most studies represent it as weight, then what's happening is that the cell-free DNA seems to be diluted across that adipose tissue. So we have seen this as well in our studies, in our clinical testing. We're trying to take a deeper dive into that. And even if you wait longer in the gestation, until maybe if you get into the third trimester, you would then get a sufficiently high fetal fraction. What we've seen in our limited cases to date is that we aren't able to overcome. If there's initially a low fetal fraction, sometimes we can get a result, but often we can't, unfortunately. So this is a study that was done, it illustrates the fact that criteria for specimen rejection is clinically important. So this was a study that was done, I like the title, The Performance of Non-Invasive Prenatal Testing When Cell-Free DNA, Fetal DNA is Absent. What that means is they used non-pregnant women, and they sent DNA from these women, or they sent samples from these women to commercial labs. So they had 2 healthy non-pregnant women. They sent samples to 5 different commercial labs for cell-free DNA prenatal screening. This is an imperfect study. So it was 2 patients sent to 5 labs. By the way, they did lie on the requisition. They said that they were pregnant on the requisition. That's not great practice to do. But nonetheless, it was a letter to the editor. It is a proof of principle. There were a lot of commercial labs who were not reporting the fetal fraction even when this was published. And there's still some that aren't. But it is an important checklist. It's actually a checklist item on the CAP checklist. And it's an important quality control piece as well. But what they found when they did this is that 2 labs did not give a test result. And they said, we can't tell you because the fetal fraction is too low. 3 labs did. Okay? So only 1 of those labs reported the fetal fraction, which was low. So patient 1 here at 4.3%, patient 2 here at 3.9%. And then these 2 labs did exactly what I said. Looks like 46XX to us. We can't see any aneuploidy. That's good. Mom doesn't have any aneuploidy. But obviously, it's an illustration of the fact that that is an important quality parameter and one that we certainly use in our clinical testing. Statistics. I'm going to show you some data, and we have to talk about Z-scores. So the Z-score is a representation of the standard deviation of a sample relative to a population. And I'm not going to show you any equations. As soon as you show equations, people's eyes glaze over more than they normally would at 4:05 on a Wednesday afternoon. But the point is that the Z-score is a representation of how closely your sample is to a population. That's enough information. So Z-score of 0 means that you're in the 50th centile. And then from there, as you get to either negative Z-scores or positive Z-scores, you can see that that's a significant, a minority of the population. What's published is using a plus or minus 4 Z-score. I'm going to show you data about what that actually looks like. So that would correspond to 99.997% of the population with a Z-score of plus 4. Because I did go to undergrad at Carolina, basketball is what's in my heart. And so I have shown you here the height for Shaquille O'Neal. Okay, college player, not a college player, professional player, former professional player. But you can see where his height would be. And so that corresponds to actually being taller than more than 99% of the population. So when we're talking about a Z-score of plus or minus 4, that's a significant bar. Okay, that's a very much, in a normal population, just the very tail ends of it. Okay? Okay, so just reminding you, we take a chromosome and we divide it into big bins and into little bins. Chromosome 1 is big, chromosome 21 is smaller. So what we're doing with our statistical tests, we're going to flag large bins that have a Z-score that's either above or below 4, so above plus 4 or below negative 4. We also look at whether there's contiguous bins that exceed a Z-score of plus or minus 4. The reason we do that is because what we're trying to detect is aneuploidy, a whole chromosome or a large portion of a chromosome that is at either an increased copy state or a decreased copy state. If the neighboring bin doesn't exceed a Z-score of 4, then we flag it. Because if you have a whole chromosome alteration, you shouldn't have one bin that's above, and then one bin that's below, and then another bin that's above. That's suggesting that something might be going on with that sample or with the analysis. So here's what the data looks like. This is a relative chromosome 18. And so what we've done here is flip. I'm showing you a flipped chromosome 18, so the P arm and the Q arm. And so this is showing us the 1 megabyte windows, so starting over here at the P arm, and we just are dividing it into all of those little bins marching across chromosome 18. This is an example of a euploid fetus with a predicted fetal fraction of 19%. And all of the blue circles are indicating that those Z-scores are less than 4. So if they're less than 4, we're going to get a blue circle. And as we would like to see in statistics, sometimes you're above the mean and sometimes you're below the mean. Randomly, you should be above and below, right? Thinking back to Westgard rules. If we have a case of trisomy 18, it doesn't look like that. So this is a predicted fetal fraction slightly lower at 16%. Note that the scale has significantly changed here. So the lowest that you can see is actually a Z-score of 2, and it's going up here to 8. The red squares, those are indicating that we have exceeded that Z-score of 4, and we have a lot of them in a row that are exceeding a Z-score of 4. I think that's intuitive. If you have a case like this, I can comfortably say that this is trisomy 18. And we did in this context, and that was diagnostically confirmed. Sometimes we see bins that are flagged, they have a Z-score above 4, that don't correspond to an aneuploidy. So this is a euploid fetus that had nothing on chromosome 19, no flagged bins. This is another euploid fetus that had a single flagged bin. So that's when it gets the red triangle. So that's telling us that we had just one single large bin in isolation that was above a Z-score of 4. So is this an analytically real event? Probably. Is it clinically significant? Well, mom made it to adulthood. She's fertile. So it's not corresponding to an aneuploidy that's present in the fetus. So we all have thousands of benign copy number variations, and that information will come out. And if it's larger than 1 megabase, we would see that in our test. So this is an example of what we would not call. And just as an aside, chromosome 19 is really noisy. For whatever reason, we see a lot of variability in chromosome 19. That's information that would be helpful to know, for example, when you're developing a test, but has never been reported by any of the commercial entities in that space. So what we quickly noticed, though, was that using this Z-score of plus or minus 4 is insufficiently sensitive. So to maximize sensitivity, we also needed to do a per sample statistical test. And for this, again, we're looking at chromosome aneuploidies. So we're starting with what has the highest clinical utility. And so we look across that entire chromosome for all of the chromosomes, not just those that we're going to call aneuploidy for. And we determine the mean Z-score for the whole chromosome. And then we compare that chromosome to, on a per chromosome basis, what's in our baseline. So we've sequenced 400 plus samples, their chromosome 18s, and we know the natural variability that we see in that chromosome. I mentioned chromosome 19. It has a lot of variability. Other chromosomes have less variability. And so we then set thresholds based on our validation data using both dilutions of samples and, of course, known positives to classify whether there's an aneuploidy that's present or not. So here's an illustration of when that becomes important to do. So this is a euploid fetus. So we're looking across the chromosome 21. Remember, it's smaller, so we have fewer bins here. And again, P arm over here to Q arm, and no flagged bins. It's sometimes above and sometimes below, as we would expect in a euploid fetus. And then if we look here, at first glance, you see that there are some bins that are below, but actually relative to that 0 line, it's above, right? So it looks like there could be something that's going on here. Do you want to call it trisomy 21 based on this data? Because I don't. We did another statistical test. This was a lower fetal fraction, in this case of 6%. And there's numbers. So looking here, this is our per chromosome analysis. So these are, I've just shown you a sampling of chromosomes, highlighting here specifically chromosome 21. So the sample, if we looked across all of chromosome 21, the mean Z-score was 1.13. So that doesn't sound that significant. But it turns out that for chromosome 21, the standard deviation on average that we see for that chromosome is about somewhere around 0.25 or so. So we flagged that you should review something if we get a sample Z-score of 0.89. And then 1.04 is when it's actually classified as abnormal. So this sample was confirmed to be trisomy 21, and it was a really nice illustration for us of knowing what our limit is. You might notice that it's also classified as abnormal for the X chromosome. That's because males have a single X chromosome. So the analysis just tells you whether there's one or more. This is reassuring that we have a loss of the X chromosome when we have the presence of Y chromosome. We also do call sex chromosome aneuploidies. Okay, so our clinical testing is in production. It has been since May 1st of 2017. I have to give kudos to Bryce, who worked with me, because I didn't want to have what I call, and the trainees know this, when you come to rotate with us and you look at Oncoplex, I call them our spreadsheets of doom. They have 12 tabs, and there's thousands of rows in these spreadsheets, and it's hard to analyze. Here's our data for this test. This is our top-line data. You can delve in more, and you can get some more information from it. But we have what we need right here. So we want to look for the mean coverage. Is there enough coverage for us to tell you whether I can adequately call that sample or not? And if not, it's going to be red. So we even have color coding that's present. What the predicted fetal fraction is, remember that's based on that size difference that we have. The calculated male fetal fraction, the sex classification, and then the autosome classification if we see any abnormalities or not. And so you can see when things start to get red, this was an example that had what appears to be trisomy 21. And then this was a sample that had what appears to be trisomy 16. Over here in orange is if we haven't met our required characteristics. So we have Y chromosome that's present in the sample because it's about 3% of the sample. You can see our prediction actually is saying that it's 6%. That's wrong. Okay? So the Y chromosome in this case is more accurate. And if you compare across here, we see that they're on average pretty close, but not always. And that's because that's why we call this very clearly a predicted fetal fraction. So it's a relationship. It's imperfect. Thinking about the bioinformatics, we also stamp our reports with every single version of the pipeline that we're using. And that's really helpful when you want to track back to when did I do this analysis? What baseline were we on then? What had changed about the pipeline in that context? So it's a really nice view. Also really nice for me when we're thinking about our testing is that our turnaround time metrics. I can actually measure something in hours in genetics. We can never measure anything in hours, but if we look from when you collect the sample to when we receive the sample, on average, that's 7.5 hours. We don't get to do that in genetics ever. Oncoplex is a 4 to 6 week turnaround time. So this is nice. And then thinking about the mean time from collection, again, to result, 6 calendar days. Now, I don't want to advertise this too loudly, but the genetics lab, we don't work on the weekends. Okay, so we're only open like 7 a.m. to 7 p.m. is when we're staffed from Monday through Friday. So to have a 6 calendar day on average turnaround time, there's a couple samples out here that were a little bit longer than that. That's doing pretty good, right? Sometimes our bioinformatics for Oncoplex can take 3 to 4 days. Here we had to change all of those parameters, everything from when we received the sample all the way through. So we do 2 runs of our genome sequencing for prenatal testing per week. And thanks to Fong and Bob who pulled this data for me. So we've done approximately 500 tests since May. For us, that's a lot of tests. Clinical chemistry, not even paying attention to that. But what we've seen since May, 93% of our samples have been screened negative. That's the language that we use. That's the language that we developed with our providers here. So Erin helped us with this. Whitney helped me with this as well, and then Edith Chang in MFM. We really worked closely to develop the language. So what we say is a screen negative, and that's very intentional that it's a screen negative, right? So this is still a screening test. We don't want, it's really more here. When we're saying a screen positive, we want that right off the bat to be staring at you in the face, that we have a screen positive, but it's just a screen. So there does need to be diagnostic testing on top of that. Indeterminates, so that's about 5% of our samples, and so that actually corresponds to about 21 samples that we've seen. Some of those are women who've sent us the sample more than once. We've gotten one sample from one woman 4 times, so we're tracking that a little bit more closely now. No, unfortunately, none of those times could we get a result in that specific context. But about a 5% indeterminate rate, that's consistent with what commercial labs who do issue an indeterminate result. So that's in the range of sometimes 6 to 7% is what's published for other laboratories. So that for now seems acceptable. We've had 11 screen positive cases. So remember I said 500, we've done about 500 samples. If you're thinking back to prevalence of these disorders, it's about 1 in 500 and then going down to 1 in 1,500. So that's a really high prevalence rate. That's because how people are using the test. Sometimes we're using this test after you've gotten a maternal serum screening positive result. Those aren't necessarily what the guidelines are, but sometimes that's patient preference. And sometimes patients don't want to go on to do diagnostic testing. Remember, it does carry a small but definite risk if you're doing chorionic villus sampling or amniocentesis. So what we sometimes see is women who are in their second, or we've seen as late as 26 weeks, where we're still doing this cell-free DNA screening test. The nice thing is, it's fine for us. We actually get a higher fetal fraction. We can be more confident in our result in that context. So we've had 6 trisomy 21 cases, 2 trisomy 18, 3 monosomy X, and 4 of those cases to date have been confirmed by diagnostic testing. A big thank you to Whitney, because she helps get all of us coordinated on the diagnostic testing piece of it. This test was sent to this lab, this test was sent to that lab, and it's really important for our QA and saves us from having to constantly go back in the medical record and see if we know what's happening. Looking at what that data is as far as relative to the predicted fetal fraction in the chromosome 21 mean Z-score. So the cases that are the red squares versus the green triangles, these were our validation cases relative to our production cases. So you can see some of those Z-scores are pretty low. And that's why we're doing, again, our second statistical test to know if we have an abnormal. We have not yet had a case that was confirmed to be a false positive for trisomy 21. There's a lot of biologic variables that you have to think about with cell-free DNA prenatal screening. And pre-analytical variables is near and dear to my heart. That's actually how Colin and I met, talking about microRNA pre-analytical variables. But we don't know much, and this isn't a sexy topic when you're thinking about the field at large. What we know is that for maternal factors, higher maternal BMI corresponds to a lower overall fetal fraction. You can certainly have occult maternal malignancy, so mom has cancer that she doesn't know about. There were some early papers that got a pretty significant amount of press where that wasn't known that it could happen. But tumors release cell-free DNA just like you get from the placenta, and you can't tell the difference. All you can tell is that you have an aneuploidy that's present. When we're doing our analysis and we see potentially that there's multiple copy number alterations, that's when we might be more suspicious. There can also be, actually this is the most common, maternal mosaicism, often for sex chromosome aneuploidies. Mom has no idea. She is mosaic. Obviously she's fertile, or there could have been an egg donor. If mom has any sort of chromosomal abnormalities as well. Thinking about placental or fetal factors, that includes confined placental mosaicism. So in one region of the placenta, you have an aneuploidy that's not present in the entire placenta. It could be present in the entire placenta, but not be present in the fetus. Both of those would have a similar result as far as flagging positive, analytically real with what we're detecting, but not reflecting what's going on in the fetus. If you have a placenta that's still remnant from a vanishing twin, of course, if you have true fetal mosaicism, the fetus itself is mosaic, we would have no way of knowing that because we're just en masse sequencing all of the DNA that's coming from the placenta. And then a low fetal fraction does correspond to an increased risk of trisomy 13, 18, monosomy X, and triploidy. So in those conditions, you have a lower fetal fraction overall that's getting released into maternal bloodstream. To me, this is counterintuitive. If you have a process like an aneuploidy, trisomy 13, 18, monosomy X, you'd think there would be more cell death. So you'd be releasing more of that DNA into mom's bloodstream. That's not what happens. So in these contexts, it's not. In trisomy 21, it is. So just to keep it interesting, it's different for different aneuploidies. So the most common causes of false positives and false negatives, so in confined placental mosaicism, that would often be a false positive. So you have an alteration that's present in the placenta that's not present in the fetus. Maternal malignancy, the copy number variance in the vanishing twin. And then anything that's causing a low fetal fraction, so gestational age. So right when that study I showed you, if you're sending a non-pregnant woman, then hopefully the fetal fraction is going to be low. The cell-free DNA is going to be low in that context. Or if you have any sort of a biological context. And we talked about increased maternal weight being another factor that decreases that overall fetal fraction. This was an article from the Boston Globe that was published in December of 2014, and it has a video. I just took a still shot here. It's a catchy title. It's going to catch your attention. So there have been some studies that have looked at this as far as people who are acting on cell-free DNA screening results without doing diagnostic testing. And so from one study that is the best public, or at least the most widely available, they had the most numbers in it, it was about 6% of pregnancies that didn't have diagnostic testing that just terminated without doing any additional follow-up. And what had happened for this specific couple is they had been told that their child had an aneuploidy that was incompatible with life, and that was a false positive. Right? There's reasons that you can have false positive. I didn't even mention you could have a mix-up in the laboratory. That's another reason you could have a false positive. But they did elect to do diagnostic testing, and part of what the article is pointing out is that we haven't sufficiently educated our providers. This test just came online in 2011. I've already told you we don't exactly understand all the biology that's going on with this testing. So we've moved very rapidly into a high clinical adoption rate without having really the tools at hand. And again, that's part of why we think that it's important for us to be offering this here for our patients so we can provide that clinical interpretation. Unexpected things that we found. This is a case of suspected occult maternal malignancy. This is a woman who was having cell-free DNA prenatal screening. You can see we have a big peak over here in that 147 base pair range, which corresponds to not just fetal DNA, that's where circulating tumor DNA lives as well. So if you have an abnormally proliferating cell population, like cancer or a fetus, that's when we tend to see this type of a population that would be at 147 base pairs. Looking at her sample, I don't think you need me to tell you that there's a deletion here on chromosome 7. And this is a lot of bins, right? This isn't just a 1 megabase region. This is a lot of megabases across chromosome 7. And the specific region of chromosome 7, 7q minus, is associated with myelodysplastic syndrome. That was not known in this specific patient's history. And at the time, she didn't want to follow up on that. She has autonomy and she gets to choose what she does. We provided the information back to them. And Erin actually had to have that conversation with the patient, and those are difficult conversations. We had another unexpected result of a trisomy of chromosome 16. Now we're validated for 13, 18, 21, X and Y. 16 is not in that mix, right? But trisomy 16 is actually the most common fetal aneuploidy, right? The reason that we're not usually testing for it is because it typically spontaneously is lost early in the first trimester. So this was a little bit later in the first trimester, and well, we were a little bit stuck when we saw this result. What do we do with this? And so there was a genetic counselor that was involved in the ordering, and so there had been counseling that had happened at that point in time. And then the patient was coming in. I'm picking on Aaron's cases. The patient was coming in to see Aaron the next day, and it was completely clinically concordant with the presentation. So it seemed that this fetus did in fact have trisomy 16, and that was information that we did put onto the report so that it was available in the medical record as a finding that we observed in a non-validated context. We have also seen cases of confined placental mosaicism. So this is on chromosome 22, the normal up here. In this specific case down here, you can see that there's a large region that seemed to have a copy gain of chromosome 22. This case did in fact have diagnostic testing, partially because of the report that had been issued at an outside laboratory that erroneously called trisomies. And it was only in the placenta. So the fetus was totally normal. So this is a case, though, where we would see that we have an abnormality. We have no way of knowing, right, if it's confined placental mosaicism or not. And that's when we start to have a dialogue with the ordering providers. There's currently not great consensus regarding cell-free DNA for prenatal screening. So I've bolded the areas where there is consensus, which is that you should have counseling before you get the test and after you get the test. That's a great recommendation. And so all of these professional societies agree with that. Whether to offer this screening to all women or not, we haven't gotten there yet. Whether only to look for the common aneuploidies, still not consensus on that. Laboratories are certainly, it's a nuclear arms race, just like in every other area of genetics. The more you do, the better your test must be. There's definitely this feeling that that's the case. We have not elected to go that route to date. But professional societies do agree that the screen requires confirmation and that no management decisions should be made from the screen, which we would certainly concur with. We're looking for trisomy 13, 18, 21, X and Y, sometimes some microdeletions, duplications. We can see if there's trisomy 21 as well. What I can't tell you if there's any open neural tube defects. That's not some information that we get out of this test. There's a lot of other causes of fetal demise that will not be detected by this test. So one thing that we do recommend is that you should get an AFP to look for open neural tube defects. Maybe they're going to be getting a first trimester ultrasound. There's other ways to screen for these things, but the point is there should be screening that is outside of this. This is not a replacement of all prenatal screening methodologies. And we're only testing in singleton pregnancies, not in twin pregnancies. So here's what a positive screen result looks like. And I just want to highlight specifically over here the comments that it doesn't assess for open neural tube defects. It's a screening test, false positives, false negatives. You have to use clinical correlation. In case that wasn't clear enough, don't make any medical management decisions based on this result. And we do offer that you can do sex chromosome aneuploidies plus or minus. You can get a report back for the sex chromosome or not. If we detect a sex chromosome aneuploidy, we will report that back. So there's a lot of areas of growth that we have looking at the fetal fraction prediction. It's currently imperfect. We want to expand our aneuploidy validation to some of these other rare autosomal trisomies. And then we're going to be talking with maternal fetal medicine about going from the full chromosome into subchromosomal events. And I already mentioned this, just to reiterate, we're doing this for better patient care. To support our research, we're taking innovative approaches that are different. In an education, our trainees are the first ones who are getting access to this because we're the first academic medical center who's developed our own test. This isn't training that anybody else anywhere is going to be getting. You can do the test in collaboration with a commercial company, but that would be a different context. So there's a lot of people to acknowledge. I will let you read this. I apologize that I'm right at time. I'd be happy to take at least one question and happy to talk as well afterwards. Thanks so much.
I have a biological question.
Yes.
So this placenta and fetus is very small.
Yeah.
Is much bigger than that.
Yeah.
Why is there 25% of the cell-free DNA that is from this tiny little thing? What is it about the biology of those cells that does that?
Right. Yeah. So the question is, so a small fetus, very small at 10 weeks, relative to a very large mom, and so why is so much of it coming from the fetus placenta, but we call it fetal? I think it's because of the proliferation. There's a reason that Dennis Lowe compared this to cancer. So you have an extremely active proliferation process that's happening. A lot of remodeling, if you think about embryonic development, that's likely what it seems to reflect. But yeah, there's a lot of it that's present because it's so rapidly cleared, whereas mom isn't turning over that many of her blood cells at any given time relative to that explosion of growth that's happening in the fetus.
I think we're out of time.
We have one more question?
One more question.
Do you have any mechanism to identify false negatives that you might be getting?
It's a great question, Susan. So the question is about false negatives. And so this is something that we're very interested in. Again, thinking about our patient population, we have much better follow-up, right? If we have a screen negative and the woman delivers within our institution at any of our entities, providers are going to be motivated to tell us that there was a false negative if it wasn't identified until delivery. So I think that's going to help us get a better sense of that. We know that false negatives are out there, despite that data that I showed you of all of these hundreds of thousands of women. Remember, there's a bias in what's published, and these are commercial entities that are doing the testing and publishing the papers. So I don't think we have a great handle on that. So some individuals here at the U have looked at this. So Jay Shanduri and Hillary Gamble and others have actually looked at the false negatives. We haven't found any yet. We've tested a tiny portion of pregnancies relative to what there actually is for pregnancies that are being delivered. So thanks so much. I'm sorry again about questions, but I'm happy to answer any down here.